Hello viewers and welcome to a new STM32 World tutorial video. Today we are going to talk a little bit more about timers, specifically how to use a timer to generate pulse width modulation on a pin which doesn't have an attached timer channel. Now, before I go into that, let me I actually thought I made this video already, and the joke is that for years I've been following an Australian guy that is doing an electronic engineering video blog called EEV blog on YouTube, and I always laughed at him. He regularly in a video say, "Well, I think I made a video about this before, but can't remember what video it is." Now, Dave have made about 1700 videos over the years. I mean, it's a lot. In comparison, I have made probably around 75 videos, maybe 80 videos on my STM32 World channel, and I can't remember if I made a video already. So that's a bit, I don't know if it speaks about me or it speaks about how hard it actually is to remember. But the interesting part is that I started producing these videos, let's see, tutorial video 1, 11 months ago. But before that, I actually posted a couple of videos about BITBANG PWM, a couple of shorts. But I realized I never really explained what is going on, and it is actually quite interesting. It's a timer, a use of a timer. So a little more background. One of the most popular development boards, apart from the Nucleo and stuff like that, is the Blue Pill board. I absolutely despise the Blue Pill board, not because of the board itself, but because they're all fake. None of them these days have STM32 F103 MCUs anymore, but I mean, and that gives especially beginners a lot of problems, so it is completely pointless. But all these boards, and I don't know if it was a Blue Pill that started this or why it is that way, but they always have a LED. It's down here, PC13, which is, well, I mean, the LED, they always have a LED on these boards that are hanging off of PC13. This was carried over to the Black Pill board some years later, where they also have a LED hanging off of PC13. Now, the problem with PC13 for this is, if we go in, well, it was obvious from the pinout, but if we look at the what PC13 can do, you can see, well, it can act as an external interrupt, but it doesn't have a timer channel connected to it, and that means you can't run pulse width modulation from a timer on that pin, which means that you can toggle this pin on or off, the LED on and off, but you can't dim it. You can't control the intensity of the LED by using PWM. That PWM on a timer channel has been covered in 3 or 4 of my earlier videos. Go back and find them. It's I might even link them in the description down below. However, on PC13 you don't have that option. That at some point, obviously, about a year ago, since I made a couple of videos on it, led me to think, why not? Can you BITBANG pulse width modulation, and what would that actually require to do that? Now, BITBANGing is essentially used where you don't have a supporting peripheral. There has been people BITBANGing serial protocols, BITBANGing I2C if you don't have an I2C peripheral, but it is giving an enormous overhead because you have to calculate everything and do everything in the core MCU executing code, and I wanted to see, can it actually, is it possible to BITBANG pulse width modulation, and if it is, how much overhead does that provide? Now, it's pretty obvious. If you want to bit bang a timer, we need a bit bang something, a pulse width modulation. We need a timer. So this is my F405 configuration. Clock has been configured. Debug port and UART has been configured, and I have configured PC13 with a LED, which is on the board. Now, if we look, I have also configured a timer, and I just picked timer 4. I have set the prescaler to 84. The timer boss clock is running at 84 megahertz. So by dividing that with 84, I get down to 1 megahertz. That's just easier to calculate in my head. And I further divide that down with a counter period of 50, which end up with, if I can do the math in my head, about 20 kilohertz, 20,000 times a second. And the idea is, if you run an 8-bit counter on that, you further divide it with 256, that ends up around 75, 78 hertz or something like that, which should be quick enough for us not to be able to see the on-off, but just see it as a dimmed LED. If you remember from, back in the movie days when you went to a movie theater, the frame rate was back then 24 frames per second. So if you get up around 50, you can't see your eyes cannot detect that on-off sequence in any way, shape, or form. So we have a timer here. The timer is just running with a counter period of 50. And that is it. Now let's look at the code. Here we go. Let's start with nothing. Let's fire that up and let's run it. I have played around. I found my old code, so I have this already. So let's look at the serial output here. It starts there and it's running almost 21 million times around that main loop. And all it does right now is that once every second, it prints out that loop count and reset it. And that is all it does. And if we look, this is a little hard to see, but if we look at the device, you have the middle board is actually the MCU board, and it has 2 LEDs, and it's a little hard to see because of my shitty camera, but the right LED, which is blue, I believe, is off at the moment. And if we look in here in the, I need to go back there. If we look in here, you can see that by default, the GPIO is high, and that means the LED is off. It's reversed. So that is the starting point. Now, the first thing to do is to fire up that timer in interrupt mode. And we had this up here. So this will generate an interrupt every with a frequency of 20 kilohertz. And by default, the STM32 HAL libraries will call handle the interrupt and then call a callback to handle that interrupt. Now, what we are going to do is we are going to have a PWM counter, which is here. That counter will count from 0 up to 255, and then it will wrap around and go back to 0 and count up again. We also have a PWM value, which we set to the value where we want the duty cycle of the pulse width modulation. So in this case, I set it to 128, which should give us a duty cycle of 50 hertz. Or 50%, sorry, 50%. So the only thing left to do is actually to write the callback, and let's put that here under in the code 0 section. And this is really simple. So all we're doing, we're not checking the timer channel because it's the only one we got running, it would be correct to check that it is timer 4 channel. But I'm essentially just increasing that PWM count. So since it's an 8-bit value, it'll keep going up to 255, then it'll wrap around to 0 and go up again. Then I use the shortcut if then else syntax here to set the BSRR register on a port is basically set a single bit on or off. And basically I'll say if PWM count is bigger than the PWM value, then I will set it. I'll set that bit. That means the LED will be off. If it is less than the PWM value, I will reset that bit. That means the bit will be 0 and the LED will be on. Now remember, I set the count up here. Let me see, I'm starting the timer, that's it. I set the count up here to 128, so it should be about 50%. So let's... Oh, that didn't work. Device back, we have it there. I am going to run that code, and you should be able to see that LED coming on the middle board there. You can see it is on a bit. Oh, what? I have some problems here. Let's try to verify that this is, let's try to set this. No, let's do something else. I actually had the code down here originally. I basically have, I change that PWM value every 10 milliseconds. So here you should see the LED pulsing. So let's run that, and let's go over here and let's look at the device again. There you can see it vaguely, and again I apologize for my somewhat poor camera, but you can see that it is possible to pulse the intensity of this LED. It looks better for real than it does on the camera. So let's go back here and let's remove this check down here, because I want to look at what does this actually do performance-wise. Now, okay, let's start by saying if we don't start this timer. So I want to see what does it cost to run this in the background. So let's try to, oh shit, I forgot to go back to this. So I essentially disable the timer start and that change thingy. So let's fire this up and let's look at the serial output there. So it runs approximately 21 million times around that loop every second. Now if we start that timer, that means we are doing that thing in the background. Let's see what that changes here. So 20,990,000. So now it's go 20,060,600,000. So it drops about 300,000 loops per second, which is actually not all that much. And all we are doing in this is we are increasing a counter, and we are setting this set reset register in every loop count. Now let's dig in a little deeper in this, and what we can do, and this is another point of making this video, is to actually look at the profiling data of this. So rather than running this as we did just now, let's try to fire it up in the debugger. There. Here we go, statistical profiling. It's capturing data and it has been configured in here. So let's try to run this with the profiler capturing data. Yes, there. And let's just verify on the serial output that it is actually doing something, and it is running right now. Yes. Note for myself is, no, it's okay. That should be enough. Let's pause it and let's look at the profiling data. So now it's paused and it's not running. So it will say the main loop is actually 98.2% of the time it is spending in the main loop. Remember that number? Remember that number? You see the interrupt handler, underlying interrupt handler, is spending 1% of the time, and then you can see my period elapsed callback, which is where I'm doing this stuff, is spending 0.2% of the callback. But you'll see that it spends an enormous amount of time in the IRQ, well, not an enormous amount of time, but it spends a significant amount of time in that IRQ handler. So what I was thinking is, can this be optimized further? And in order to do this, we need to dig into how is this code actually being done. Now, if we go in and we look at the core source interrupts, that has been generated. This file has been generated by STM32 CubeMX, and one of the things you can see is that it will generate this timer for IRQ handler, and that all it does is it's calling a generic HAL timer IRQ handler with the timer as a parameter. So let's have a look at this code, and this is where HAL sometimes maybe gets a bit too chatty. Now, this is the IRQ handler, and remember, this IRQ handler have to handle all timer cases, whether you want to, I mean, there's a lot of different things that it does. So it checks for comparators, it checks for a lot of things, and actually the only thing we're using handles after all these codes. Where is it? Here. No, that was capture. Period elapsed callback. Here we go. So actually, this is of all this code, which is being executed on every single timer interrupt. That was the 1-point-something% you saw. We're actually only using this part. So what I was thinking is, well, why don't we simplify this a little bit? And this is actually where I used a feature. Somebody made a comment on a video early on, one of the timer interrupt videos. There was a comment saying, but you can actually configure in CubeMX, you can say don't generate that callback code. So I was looking at the NVIC configuration in here, and you actually have, of course, here we have enable the global interrupt, but over on code generation, here you can see that it actually generates, let's see if we can make that a little bit, it generates, can we actually get to a point where we can read this? It's not always the best interface. Anyway, I want to generate the init enable this, but I'm not interested in the callback, and I am not interested in the generate this timer interrupt. So let's try to generate the code here. There we go. Now we generated the code, and actually if I ran it now, I can't be bothered, but if I ran it now, it wouldn't work. But if we look into the interrupt configuration here, you will see that that part of the code, the interrupt handlers, is no longer there. So it is not actually generating that timer interrupt anymore. So we have to handle that ourselves. Now, it is actually configured. If we go into this, is the interesting part. If we go into the startup code, the interrupt vector is actually configured in here. Here, I don't know where it is. Timer. I must have missed it. Here, timer for interrupt handler. It is in here, it's defined, but the code has not been generated. So if my theory is correct, all we need to do is to, first of all, we can comment this out. And then I wrote this already, so let me fetch this from another window and let me copy this in here. So here's how I end up doing it. Now, remember this actually, well, I call it time 4. Yeah, okay. So essentially what I did was I took the relevant part in here from the HAL library and I removed all the rest. And what I'm doing here is essentially I'm checking if this update flag is set, and if the basically if the update flag is set, I'll clear the flag so the interrupt can handle again, and I do exactly the same as I did before in my callback. Now it's at 110, so if the LED comes out on at all, that means it's working, otherwise it would be off. So let's try to run this first and verify that it is actually working. There we go. Let's start by looking at the serial output. There. So it actually runs already a little bit faster than it did before. Remember, the interrupt is already happening. So let's look at there, and you can see the LED is glowing dimly. So it is actually still working. Now let's look at the profiler for this and see if this has improved the situation and all. So let's try to fire up the debugger. Here we don't need to enable that again, it is already. So we go to our statistical profiling. We let it run for about 10 seconds or something like that. To 10, there, we're good. And let's pause it here and let's see. So it went up from 98 I can't remember, 4. I asked you to remember, but you can't talk to me, so that doesn't help. And you can see now it spent 0. Before it was like 1.5–2%. It spent in the interrupt handler. Now we have optimized that down. Now I am quite sure. Oh hell, I'm going to try it. Now this I have not tried before, so if this doesn't work, it might be completely far-fetched. But since I'm pretty much sure that this interrupt will only happen if these conditions are set, I think what we can do is we can comment this out and we can comment this out. So I just assume that this is the case. I clear the flag, I do the stuff, and I go back online, go back again. So let's try to run that. Number 1, let's check the output. Yeah, it is faster than it was before. Now let's look at the device. The LED is on a bit. Now let's run that in the profiler. Here we go. Statistical profiling, fire up, let it run for 10 seconds-ish. Let's pause. So we are down to 0.3% of the 0.4%, sorry, of this in order to bitbang PWM without the use of a timer channel, but still, of course, using a timer, it takes 0.4% of the MCU. So it is 0.4% that is wasted doing this, but compared to the overall, it is actually a very, very small number. It is fairly efficient. I had a little bit of code here to actually change this PWM, and if we try to run it with that, and let's see the device here. There. You can see this is the one where it actually pulses. It changed that, but I am sure if we look at the output and see it drops almost 5 million, so it's actually a lot more expensive just to play around with this because I execute this so often. So that is pretty much all I wanted to say. So we've been going through 3 things in this. Is it possible to pulse width modulate on a GPIO where there is no timer channel? And yes, it is, and it is not all that expensive. Number 2, profile this to actually prove that it's not so expensive. And number 3, can it be optimized further by not using ST's STM32 Cube MX and STM32 HAL callbacks, and just write our own interrupt handler specifically for this interrupt 4. And we know if we're not using the timer 4 for anything but this, which in this case is what we're doing, then we don't actually need to do all these checks at all. We can just clear the flag, next, right, and increase my counter as I did before, and same technique, use the BSRR register to set or disable the register. So I think this is as optimal as it can get. And this, actually, I want to finish by saying something about this. Now, I had a lot of comments over the last year. I said, why don't you do low level? Why don't you do bare metal? But I like HAL, and I don't really see any point of doing low level and remember all these register addresses, and I just can't be bothered. I'm too old for that. And I don't think it's a problem to actually use HAL and write things. And then what you need to do is you run the profiler, and if you have performance problems, as you can see clearly here, it is not a problem to bypass HAL, and HAL is doing the rest because I can't really initialize an UART better than HAL. I don't really want to deal with having printf to go to the UART and all that. I mean, I can't do it better than ST can, but in this case I could shave up almost 1% of the CPU cycles by just optimizing that IRQ handler, where because this gets executed 20,000 times every second, it spent a lot of time in this, or it spent some times in this, and having 3 consecutive function calls. First the vector goes to that, and then that will execute the HAL timer, the HAL IRQ handler, and then the HAL IRQ handler is calling the callback. So it was actually 3 consecutive interrupts and returns, function calls and returns, 20,000 times a second, and a lot of time was wasted in that. But again, use the profiler, get used to using the profiler, and the fact that we have the profiler here in STM32 Cube ID is absolutely brilliant, because you can see, in fact, let's run it again because it is really quite cool. Here we go, statistical profiling, run. It doesn't update live, you have to pause it to get the profiling data, but you pause it, and let's make this one bigger, and you can basically see, oh, that wasn't actually necessary. See, it spends 0% actually printing. It does have wait until it's, so it spends 0.01% doing the printf every second. My HAL interrupt handler is, well, about 0.5% or thereabout. And if you have a more complex, we could try to run this with the SD card or something like that. You will see that you can see exactly where the time is wasted, and then you can go in, even if you're using STM32 CubeID or an STM32 HAL, you just go in and optimize the bits that needs optimization, and you know the rest. It's like, I don't care about that. It's like, I personally don't think I could do that UART print faster. I could certainly not do printf better than the standard libraries. It would be a nightmare to get anywhere close to that functionality. So I'm quite happy with this. That's about all I wanted to say. As usual, please like and subscribe, and please comment down below what you think about this video. I mean, you're welcome. If you don't like it, I would rather hear why you don't like it than just click the thumb down. It helps me make better videos as we move along. That's about it. More timer, more pulse width modulation. I hope you enjoyed it and have a wonderful rest of the day.